Hi, it's Kate. In this video, we're going to review one of the more complicated topics that we're learning in this course, which is an application of the change of basis that we talked about earlier in the class. It's an application to dynamical systems, and it mentions the importance of eigenvectors and eigenvalues, which we'll only be using briefly and are certainly such a critical topic that we could make tons of videos about them on their own, but for our purposes today, we're just going to be working with them in a particular example. Let's get started. Dynamical systems, first of all, talk about how a particular quantity varies over time. And discrete dynamical systems, which is what we'll be working with today, are an example of dynamical systems that focuses on snapshots of these two quantities. So you have particular timestamps at which you're looking at the levels of two quantities and seeing how they change rather than immediately trying to model the changes of these quantities using continuous functions. So here's our example. It's a discrete dynamical system. We have two population levels. One is the spotted owl and one is the wood rat. And you can see right away that O of t is always going to be referring to the owl population, and R of t is always going to be referring to the rat population. And so these two functions that were given below, O of t plus 1, R of t plus 1, they're basically saying that let's talk about a snapshot in time, t. If you care to move forward 1 unit in time, for us, this is going to be years. T will be measured in years. If you care to move forward in time by 1 year, the owl population will be a combination of what the owl population was 1 year ago and the rat population was 1 year ago. So it's about 0.5 times what the owl population was last year plus 0.3 times what the rat population was last year. And then if you're talking about a rat population at a particular time, that's going to be a mix of the rat population last year, 1.2 times the rat population last year, plus negative 0.2 times the owl population last year. And the positive and negative signs on those various terms make sense, right? The more owls and rats there are, both of those things are beneficial to the owl population because owls need owls to procreate, and they also need rats to eat. Whereas for the rat population, while the presence of rats is a good thing, right? There's a positive coefficient on that rat term. The presence of owls is a bad thing because owls are a predator, whereas rats are the prey. So this is what we're seeing here, that the owl population at a particular point depends on what the owl population and the rat population have been over the previous year, 1 year ago. And the rat population at a particular point also depends on the owl and rat populations from the previous year, that both of those sort of combine to give you what the rat population will be in 1 year from now, or the owl population will be in 1 year from now. We're told that a particular vector x is going to encode the owl and rat population at a particular time. And our first job is to find a matrix A so that A, when it acts on this x of t, will give us what x is not at t, but at t plus 1. So let's set that up for a moment. What I've done here is I've just drawn a diagram of matrix multiplication. This statement that A acting on x of t should give us x of t plus 1 is basically written right here. Here's my matrix A. It acts on x of t up here, and it generates x of t plus 1 right here. Let's fill in the various components of x of t and x of t plus 1. We know just from the number of components in the input vector, being x of t, and the number of components in the output vector, x of t plus 1, that A is going to be a 2 by 2 matrix. And specifically, if we want that first component right here, O of t plus 1, to be what's generated, we know that we need to pick the entries right here in the first row of A to be the linear combination of O of t and R of t that correspond to O of t plus 1. So we're looking at this portion of the functions that have been given to us. And so that means that the component that should be right here will be 0.5 because O of t needs to be multiplied by 0.5. The component that should be right here is 0.3 because R of t is multiplied by 0.3. And that sum is going to give us what O of t plus 1 is equal to. Let's fill that in. And let's go ahead and fill in the second row as well down here, which is telling us that if we want r of t plus 1, we want to multiply O of t by negative 0.2 according to what's up here, and r of t by 1.2 according to what's right here. So we can also fill in the second row of this matrix. So that 2 by 2 matrix there on the left with the 0.5, 0.3, negative 0.2, and 1.2, that's our matrix A that does the trick. It takes x of t and maps it to x of t plus 1 according to the two equations that were given that started off this problem. Now the next part of our problem says, suppose that there are currently 2,000 owls and 1,000 rats. How many owls and rats are there next year? Well, that means that if x of 0 is 2,000, 1,000, we want to know what x of 1 will be. And so we're going to use the matrix A to act on x of 0, and it should generate x of 1. Let's do that. Here we are. We've taken the matrix A, we've had it act on x of 0, and here's x of 1, which is telling us that there will be 1,300 owls and 800 rats if you take a look at both of those entries in the new vector. The next part of this question says, what about the year after that? Well, if we're at x of 1, all we need is to have A act on x of 1 to get us x of 2, which would be the population levels after 2 years. So let's do that. I'm going to stack these matrices so that we don't have to take up quite so much space. So we see after viewing this process that after 2 years, we should have 890 owls and 700 rats. And then the question is, in t years, well, can I write down a general formula for t? So far, after 1 year and then after 2 years, there doesn't seem to be much of a pattern. So at this point, unless you specify what t value you're interested in and we can then compute it out by hand, it doesn't seem possible to write down very nice, neatly, and succinctly what the owl population level would be in t years or what the rat population level would be in t years. Let's put a pin in this part of the problem and see what happens if we change the initial values in owls and rats and see if we can figure out a way for other initial conditions for us to be able to write down the population levels in t years. So here we have the same question, but instead of starting with 2,000 owls and 1,000 rats, we'd like to start with 100 owls and 200 rats. And so the same questions follow. How many owls and rats are there next year, the year after? We don't really need to do new conceptual work. We know that if A acts on our initial condition, it should give us the population levels after 1 year. So let's put that to work on a new initial condition vector, the one that shows us that we have 100 owls and 200 rats. So here's our first computation. It seems like the population levels after 1 year will be 110 owls and 220 rats, which is interesting because both populations have gone up by 10%. So both have shown a 10% increase. Let's keep going. It asks for the year after that. Just like in the previous part of this problem, we want to have A act on x of 1 now in order for us to get x of 2. We see that after 2 years, our owl population has now risen to 121 owls, and our rat population has now risen to 242 rats, which is interesting because that's another 10% increase from the year before. So this is interesting. With this initial condition, with these initial population levels, 100 and 200, every year is going to be a 10% increase. Now, why is that the case? Let's take a look over here. We know that in order for us to compute another passing year, what we're really doing when we are taking A and having it act on x of 1 is that x of 1 itself is the result of A acting on x of 0. And we know that A acting on x of 0 was equal to 1.1 times x of 0, right? The result when we first had this matrix act on x of 0 was that the result was a scalar multiple of the original vector just multiplied by 1.1. So if you're taking A and having it act on 1.1 times x of 0? Well, by linearity, a acting on 1.1 times x of 0 is equal to 1.1 times a acting on x of 0. That's one of the properties of linearity. You can either scale the input, or the result would be the same as if you hadn't scaled the input and then waited and scaled the output. And here, when we're looking at this piece, we have a acting on x of 0 again, which we know the result of a acting on x of 0 is just going to multiply x of 0 by 1.1. And so we see that the net effect of this entire process is really to multiply x of 0 by 1.1 twice, or by 1.1 squared. Now, we could certainly figure out what x of 3 would be by taking x of 2 and multiplying it by a, but by this similar reasoning, we can see the following happens. We know that x of 2 is equal to 1.1 squared times x of 0. By linearity, we can quote-unquote factor out that scalar multiple. And we know the result of a acting on x of 0 is that it will just multiply x of 0 by 1.1, and so the net effect is that we have 1.1 cubed acting on x of 0. Remember, this was us computing what x of 3 would be, right? The result when a acts on x of 2. So when the question asks us, hey, how many owls and rats will there be in 10 years? Well, we can follow the pattern here. Let's take a look. We know that if x1 is 1.1 times x of 0, and x2 is 1.1 squared times x of 0, and x3 is 1.1 cubed times x of 0, then it seems only logical that x of 10 is going to be 1.1 to the 10th times x of 0. And after t years, we can actually put this in terms of t, that if we care about x at time t, that's going to be 1.1 to the t power times x of 0. Pretty cool, right? Let's take a look at what happens under another set of initial conditions. Suppose instead there are 300 owls and 100 rats. Now the question sort of jumps right to it. How many owls and rats will there be in t years? We want to go through the same steps and get a feel for what's happening here, similar to what we did with 100 and 200, or 2,000 and 1,000. Let's go ahead and compute what x1 would be, or what happens when a acts on this choice for x of 0. We see that we get 180 owls and 60 rats after 1 year, which happens to be a scalar multiple of the original vector that we started with. This is 0.6 times x of 0. And so as we can anticipate, we know that x of 2 would be a acting on x of 1, which is equal to a acting on 0.6 times x of 0, because that's what x of 1 is equal to, which by linearity is the same as 0.6 times a acting on x of 0 alone, which is 0.6 times 0.6 times x of 0, because the result of a acting on x of 0 is just taking x of 0 and multiplying it by 0.6. So the same pattern is happening as above, but instead of the scalar multiple being 1.1, the scalar multiple in this case is 0.6. And so if we wanted to write down what x of 3 would be, that would be 0.6 cubed times x of 0. And if we wanted to know what x of t would be, that would be 0.6 to the t power times x of 0. These are pretty special results. So let's talk about what it is about these vectors that is so unique and why they're important to this particular problem. So these special vectors are known as eigenvectors for the matrix A that we made at the beginning of this problem, and they have this special property that when A acts on these eigenvectors, the result is a scalar multiple of the original vector. So our two eigenvectors were 100, 200, and 300, 100. Now let's recall what happened to both of these. For the 100, 200 vector, which I'll call V1, anytime A acted on that, it returned a 1.1 scalar multiple of the original vector. And our second eigenvector was 300, 100. And whenever A acted on that, it took the original vector and multiplied it by 0.6. Now, those numbers, 1.1 and 0.6, those are the specific lambdas here that are... That's my cat. All right, we're going to leave that in because I think he's endearing. His name is Max, and he is quiet and asleep beside me, so let's try that again. Those values, 1.1 and 0.6, those are the lambda values associated with the two eigenvectors that we know, and they are called eigenvalues. So that's lambda, the Greek letter lambda there. And so for us, for the matrix A, our two eigenvectors are 100, 200, and 300, 100, and their eigenvalues, respectively, are 1.1 and 0.6. Now, these are two linearly independent vectors that live in R2, which means that they span all of R2, and they form what's called an eigenbasis, a basis where all of the elements in the basis are eigenvectors. And the question becomes, what use could this basis be in our original problem, the one where we had 2,000 owls and 1,000 rats, and there didn't seem to be any sort of pattern as far as how to write down what the population of owls would be as a function of time or what the population of rats would be as a function of time. Well, what's great about an eigenbasis is that it behaves like a basis because it is one. That means that any vector in R2 can be written as a linear combination of these two eigenvectors, v1 and v2. And when we ask ourselves, how do we compute x of t? What we're really asking is what happens when we take x of 0 and have a act on it t times, right? Because a, each time it acts on x of 0, moves the timestamp forward 1 year. So if we care about what x is after t years, what we really want to know is what happens if we take x of 0 and have a act on it t times, or have a raised to the t power act on x of 0, which I've rewritten over here. Now what's pretty cool though is that if you express x of 0 as a linear combination of eigenvectors, you can exploit the linearity of this transformation to your advantage. So here I've written down x of t, which is going to be the result after we have a act on x of 0 t times. And if x of 0 can be written as a linear combination of the two eigenvectors, check out what can happen. Because a acting on anything t times is a linear transformation, we can exploit that linearity and break this up into two different pieces, a of t acting on alpha 1 v1 and a of t acting on alpha 2 v2. And of course, again, by linearity, that alpha 1 and alpha 2, those are just scalar multiples of the eigenvectors, so those two scalars can be factored out as well. And we know that the result of a acting on v1 t times in this particular problem is multiplying v1 by 1.1 to the t, and a acting on v2 t times is the same as multiplying v2 by 0.6 to the t. That's their unique trait as eigenvectors, that when a acts on it t times, you can write out exactly what the result will be. It will be being multiplied by that eigenvalue t times. And so we can really write this quite straightforwardly, but the key is that very beginning jumping off point. We need to figure out how to express x of 0 as that linear combination of eigenvectors before we can say, oh, we can actually write this out as a of t separately acting on each of those eigenvectors, and that can be written really straightforwardly as opposed to that initial situation when we had 2,000, 1,000 as our initial condition and we couldn't figure out a particular pattern and didn't have a prayer of writing down what O of t would be and R of t would be. So this basis would be really, really useful if we could just figure out how to express our original vector as a linear combination of eigenvectors. And of course, that's going to require us to use change of basis. So of course, the whole point of this is that we want to put the eigenbasis to work. We want to take that original stubborn vector, 2,000, 1,000, at the very beginning of this problem, and find out how to express 2,000, 1,000 as a linear combination of eigenvectors. Once we know how to express 2,000, 1,000 as a linear combination of eigenvectors, which we're going to have to use change of basis to accomplish, by the way, then we know that computing x of t is just a matter of exploiting linearity of a. And that green box is going to be the answer to that original question that we couldn't figure out. We couldn't figure out a way to write down x of t. But if we have a way of expressing x of 0 in terms of eigenvectors, then we will be able to find what x of t is equal to. Here's that original x of 0 expressed in terms of eigenvectors at the beginning. Let's go to work. Recall from our earlier work that if we take the two eigenvectors and turn them into the individual columns of the matrix here that we've created, right here, that this is a matrix that will take us from the eigenbasis to the standard basis. But in order for us to express 2000, 1000 as a linear combination of eigenvectors, we're interested in moving in the reverse direction. We want to go from the standard basis to the eigenbasis. So that's going to require us to invert this matrix. Let's do it. There we have it. This matrix takes us from the standard basis to the eigenbasis, exactly what we want. Now we're going to use it on 2000, 1000 to figure out what the various coefficients, over here they're indicated as alpha 1, v1, alpha 2, v2, that alpha 1 and alpha 2 would be in order for us to represent 2000, 1000 as a linear combination of eigenvectors. All right, so the result of having this matrix act on the vector 2000, 1000 is 2, 6, and the significance of that is telling us that the vector 2000, 1000 is the linear combination of 2 times v1 plus 6 times v2, when v1 and v2 are our eigenvectors. So that's pretty important. Let's write that down. So we've finished the first starred point that we had over here. We have expressed 2000, 1000 as a linear combination of eigenvectors. It's 2v1 plus 6v2. So we want to now move on to this second piece right here. We want a to the t, to act on that. And here I've gone one further step, really just matching the reasoning that we have up here, which is that x of t, being a of t acting on this linear combination of eigenvectors, is going to give us scalar multiples of a to the t acting on v1 and v2 individually, and then we can actually fill in this third line here, that the effect of a to the t acting on v1 would be 1.1 to the t times v1, and a to the t acting on v2 would be 0.6 to the t times v2. Now, while this is absolutely valid, it's really nice to write this out in terms of the two components that are within x of t. So let's plug in what v1 and v2 actually are and add this out component by component. And so we can see that by plugging in what v1 and v2 actually are and then distributing that scalar, which is all this is right here, across both components, and then adding the two vectors together just component by component, we have as our final answer that x of t, the first component, is going to be 200, because it's 2 times 100, times 1.1 to the t, plus 1800, because you have 6 times 300, times 0.6 to the t. That's going to be our O of t function for the owls, right? Because that was the first component for x of t within x of t. And then our second component is going to be 400 times 1.1 to the t, because you're taking 2 times 200, plus 600 times 0.6 to the t, because you're taking 6 times 100. And that's going to be our r of t function. That's the second component within x of t. And we're done. Here's an actual, nice, straightforward formula for that very first problem that we had such difficulty finding a pattern in. And it all hinged on us being able to express this as a change of basis here, moving into the basis of eigenvectors. If you have any questions at all, please don't hesitate to ask or shoot an email. Change of basis certainly takes a long time to understand, so go slowly, label your work, make sure you're talking about which basis you're moving from and to, what you're starting in, what you're going to, and I'm sure in no time you'll be very comfortable with this subject. Thanks, guys. Just labeling those two things in case you have any further questions.